Welcome everyone to chapter 21, which is electrochemistry. All right, electrochemistry is going to build upon our knowledge that we learned about redox reactions in Chemistry 1. Now I know redox reactions are not our favorite types of reactions, but the good news in this chapter is that we know that they're redox reactions. We don't have to specify and find out that they're redox reactions. We know they are. And then all we're going to have to do is separate them out into whether they're the reduction or the oxidation steps. Right? And we can do that, I promise, as we go along. So here we have an outline of what we're going to cover during this chapter. We're going to start out by learning what a voltaic cell is. And a voltaic cell is going to be a spontaneous reaction, which we learned in chapter 20 when we have spontaneous reactions. Sometimes these are called galvanic cells. Those are just interchangeable terms. So depending on where you look them up, they might be called voltaic or galvanic. Then we're going to talk about standard voltages, right, which is given the symbol of E. And so if we see there, right, in number 3, when we have the relations between this E, that's a standard voltage. We got that little knot symbol, meaning that's standard. There's going to be a relationship between that and our Gibbs free energy that we learned in chapter 20, and our equilibria constant that we've been dealing with all semester long. Right? And then lastly, we're going to talk about another type of cell that we call electrolytic cells. But here in our first podcast, we're going to jump off by kind of hashing about what redox reactions are and what the pieces of a redox reaction are and how we can kind of spot that, and then separate them out into two half reactions, a reduction and an oxidation. All right, so this chapter is all about electrochemistry. So maybe one thing that we should do is define what electrochemistry actually is. Right? And so electrochemistry is us determining how we can use, right, chemical energy, right? And that's the energy that's stored whenever you have a chemical compound. Right? Now this could be any chemical compound. They all are storing some sort of chemical energy in them. We're going to dive more into that when we get into nuclear chemistry about how they do that. But one way that they can store energy is by their bonds. Right? And if we think back to Chem 1, when we were talking and first learning about enthalpy, right, we said that, right, it takes a certain amount of energy to break bonds, right, but it also, we can gain energy by making bonds, right, and so that energy is stored in those chemical, right, species that we have, or different compounds. And what we can do is we can convert that chemical energy into electrical energy. Remember that energy is neither created nor destroyed in the universe, but we can convert it from one type to another. And the study of electrochemistry is studying how we can go from electrical to chemical, or from chemical back to electrical energy sources. All right, and so when we do this, we have to use what we call an electrochemical cell. And there are two types. One type is the one that we said there in our first bullet point for our outline, which are voltaic or galvanic cells. All right, voltaic cells are going to take up the vast majority of our time in this chapter. Probably 90% of the time we're going to talk about voltaic cells. Right? And then at the end, we're going to bring up electrolytic cells. All right, the difference between the two is a voltaic cell has a spontaneous chemical reaction taking place, and an electrolytic cell is a non-spontaneous reaction, one where we have to put energy into the system. So we're going to study both of them, but again, we're going to focus a lot of time on voltaic and then a little bit of time on electrolytic at the end as well. Both of them are important, but we are going to spend most of our time just understanding the voltaics to begin with. All right, so let's go back and flex some of our Chem 1 knowledge skills, right? And that's here on our review slide. And this is basically, hopefully, kind of going back over some stuff that we, picked up in Chem 1. If we didn't, right, it's just going to be a little bit of memorization. I'm not the biggest fan of doing a lot of memorization, but there are certain topics where, you know what, I just have to memorize a few things. And especially here at the beginning of this chapter, there's a few things that we have to memorize. Hopefully I can give you some skills in order for us to be able to memorize those things, right? That'll make them a little bit easier when you sit down and do your exams. Right, but let's do our review here first. So we've got, remember from Chem 1, that oxidation. Right? Oxidation is where you have a loss of electrons. Right? And so remember, like we had the mnemonic of oil rig, probably. There's also like Leo goes grr, but I like oil rig. And the oil part of oil rig is oxidation is a loss. It's totally okay for you to think oxidation is a loss in your head whenever you're doing these problems, right? Whenever I'm lecturing, sometimes I have to think about it for a second because you know what? It's not intuitive all the time, right? So just, it's okay to get that mnemonic and use that as a way to remember that oxidation is a loss. And all right, so this also says that oxidation occurs at an electrode that we're going to end up calling the anode. All right, so we're going to learn two different types of electrodes. We're going to learn the anode and the cathode. And for right now, we need to know that oxidation takes place at the anode. When we see the half reactions in a little bit, or when we write half reactions, because oxidation happens to be a loss of electrons, right? What we're going to find when we look at these reactions written out is that electrons will, let's say be, I was going to write a P. All right, our electrons will be products. All right, so when we see our half reactions in a little ways, if you see an electron as a product, you can think oxidation. All right, next off we have reduction, right? And reduction is a gain in electrons. All right, and so reduction is a gain. That is the rig part of our oil rig, right? Reduction is a gain. All right, now this reduction, when we look at our voltaic cells and right, when we go through our different cells, our electrochemical cells, we're going to see that this takes place at the electrode that we're going to end up calling a cathode. All right, and if we're looking at our electrons will be reactants. When we have our half reactions, right, so they're going to be reactants in our half reactions. So if you see an electron as a reactant, right, in your head, you should say, oh, that's got to be the reduction half reaction. All right, now remember from Chem 1 that, right, for a redox reaction to occur, both oxidation and reduction have to take place simultaneously. They have to occur together. If one thing is losing electrons, then one thing has to be gaining those electrons as well. Right? The electrons just can't go out into the world wherever the heck they want to. If I'm going to say lose a couple of electrons, I have to give them to somebody and they're going to gain those electrons. They have to happen simultaneously. All right, so that'll lead us into now an introduction of voltaic cells themselves, right? And these are the ones we're going to talk about for most of the chapter. So it says that, in principle, if we have any spontaneous redox reaction, okay, so we know spontaneous reactions from chapter 20, right? They have to have a negative delta G, right? That tells us that they're spontaneous, and it has to be a redox reactions for these to take place. They can be an energy source in a voltaic cell. All right, in order for us to make these, and I'm going to have a picture of this here on the next slide, right? But we're going to have two different electrodes, right? We're going to have our oxidation electrode, which is we're going to have an anode, and we're going to have a cathode. So we're going to have two different electrodes. Those are just pieces of metal, basically. And then it says that our electrons are going to move through an external circuit from the anode to the cathode. All right, external circuit is a fancy term for a wire. All right, so basically our electrons are going to move from our anode, right, through a wire into the cathode. All right, and a good way to start thinking about some of these things, right? If you don't know where oxidation takes place or where reduction takes place, I look at my mnemonic down there. And what I say is that, right, oxidation takes place at the anode. Oxidation starts with an O, anode starts with an A. Those are both vowels. That's how I remember that. Reduction happens at the cathode, well, reduction R and cathode C, they both start with consonants. So that's a good way to remember those things as well. Okay, so let's look at a reaction between a solid piece of zinc and some copper-2 ions. All right, we're going to start with this, and then we're going to set up this exact same reaction as a voltaic cell. Here the reaction is just taking place in a test tube. All right, and so in that test tube, I'm going to mark these as 1, 2, and 3, just for us to kind of pay attention to them. So, right, each one of those has a hunk of solid zinc in them, right? That's the little piece of metal that's sticking in there. And then it's in a solution that is water and has some copper-2 cations in it, right? So it's an aqueous copper-2 solution. And notice that we can see that solution as being blue, right? And we're going to actually figure out why that solution is blue in the next chapter that we study here on Chem 2. All right. So we've got this blue copper-2 solution, and notice that after some time, so we go from 1 to number 2, notice that it's getting lighter and lighter. But yet on top of the solid zinc, there's getting to be more and more black stuff on there. All right, what that is that is the copper that were ions, and what we say is that they're plating out or turning into metal on the surface of the zinc. Right? And as that happens, notice that there's fewer and fewer copper-2 cations, and so the solution is getting lighter and lighter blue. Once you go to number 3, right, notice that it almost doesn't look blue whatsoever, right? It looks colorless. At that point, right, all of the copper-2 has gone and plated out on the solid zinc. All right, well, that's great. The copper-2 is plating out to become copper, right? But at the same time, right, those copper-2s, right, in order to go from copper-2 to neutral copper, they have to be gaining electrons. Well, the only way for that to happen, right, is for the zinc to be losing electrons and becoming zinc 2 cations. So what happens is that our copper is forming copper on that zinc metal, but at the same time, right, what's occurring is I have, coming off of that, we're getting some zinc 2 cations, and at the same time, my copper-2 is forming that solid that's sitting on there. Those two things are happening simultaneously, which is shown on our equation here, but those two things have to be happening, right? Our copper-2 is gaining electrons, right? And our zinc is losing electrons. So our zinc, right, oil, oxidation is a loss, it's losing electrons, so it's being oxidized, while the copper-2 is being reduced. And another way you can see that is like that our copper-2 is going from a +2 charge to a charge of 0. The charge went down. That's what we mean by being reduced. It's hard to see when you say, okay, oh, it's gaining electrons. Why is that being reduced? Because the charge of it is going down or being reduced. On this slide, we are actually setting up our first voltaic cell. And this voltaic cell is the exact same reaction that we saw taking place in the test tubes on the previous slide. Right? However, what we've done is we've separated this out into 2 different half reactions. All right, and so what we have is when we set this up in 2 half reactions is we're going to set it up with 2 different beakers. Over here on the far right side is a beaker that is zinc, and on the left-hand side is our copper. All right, now notice that right here we have this guy here, right, that little hunk of metal that's dipping into this solution, that is solid zinc, and that is going to be our anode. Right, over on the other side, right, over here, we have solid copper. and that is our cathode. All right, and so in the solution, this is actually some zinc 2 cations, or sorry, some copper 2 cations, and over here we have some zinc 2 cations in there. Right, those are in there, but we have those two anodes. All right, and then we've got our external circuit, right, which is a wire. All right, and notice that then it's hooked up to this voltmeter over here so we can read the voltage. And the voltage is just like the driving force for electrons to move, right? And so depending on what that voltage is, allows the electrons to move either, more readily or less readily through the external circuit or our wire in this case. And remember that our electrons are going to move from our anode to our cathode. So they're moving from our anode and back into our cathode there. So, right, notice that if we looked at that system, right, that voltaic cell, right, at that zinc electrode, which is what we call the anode, the electrons are produced. So what's happening there is that the zinc electrode itself, that is the solid piece of zinc, right, is actually throwing off some zinc 2 ions into the solution. And at the same time when that happens, it is producing, right, 2 electrons. All right, so we're producing 2 electrons. So note electrons as products. Oxidation, right? Anode. All right, when we have this, we call this electrode and we give it the sign of a negative sign. I think it's because electrons are negative and the electrons are coming out of that end. So we give it a negative sign. All right, now, number 2 says that the electrons enter the cathode, right? We saw that they flowed from the anode to the cathode, and they're going to enter that cathode where they're going to then, right, reduce our copper 2 to become solid copper, right? And again, in this case, right, note the electrons as reactants. Reduction, right, which happens at the cathode. And we say that the sign of this electrode is positive. All right, the same thing happens, by the way, if you have a battery, right? If you look at a battery, every single battery that you come across, right, is going to have some sort of a positive side and some sort of a negative side to that battery. So here I've got maybe like a AA looking battery. Up there at the top, it's positive. Down here at the bottom, it has that negative sign. When you put that in, what it's going to do is it's going to work with your electronics. So electrons, this is actually separated by 2 different sides here. Right, electrons are going to flow out of an anode side. So let's call this side like the anode side. And they're going to flow out of the negative side. They're going to go through your electronics and work them. Then they're going to flow into, right, your cathode side there, your positive side, and go back in here. Right? So a battery is basically just a big old voltaic cell. Right? There's 2 separated things where we have an anode and a cathode, and the electrons are going to flow from the negative side to the positive side. So as these reactions take place, right, notice that, right, we're going to start having more and more, or a surplus of cations are going to be building up at the anode. Right? And we're going to have fewer and fewer of them at the cathode side. So let's just say here we have this thing. So what we're going to have here, let's do our zinc 2, and over here we've got our copper 2s. All right, so one of these zincs from the actual anode is going to hop off and become zinc 2. When that happens, at the same time, right, 2 electrons are going to head this direction. They're going to keep going over here. They're going to enter that cathode, right? And what that's going to do, right, is you're going to have 2 electrons here are going to react with a copper 2. And that copper 2 then is going to plate out on the cathode itself. And so what's happening is over here on the right, we're getting more and more zinc 2s. On the left side, right, this copper 2 is plated out and becomes solid copper, so we're getting fewer and fewer of them. Right, so we've got to figure out a way to kind of counterbalance that charge. Because if we don't, then this reaction is going to happen really quickly. If we can counterbalance it, then the reaction will take place for a longer and longer period of time, which is what we're going to try to maximize, especially when we're looking at things like batteries. So what can we add to this? We can add something that we call a salt bridge. So a salt bridge, for the most part, is, right, a gel-filled tube. All right, so this is going to be this thing here in the middle. We're going to fill it with some sort of gel, right? And so what we do is that we're going to put some cations and anions in that tube that are allowed to flow. All right, so for the most part, we're going to use something like KNO3. We want to use something like K, or potassium, because it's going to become a potassium cation. And remember from our acids and base chapters that a potassium cation is going to be a spectator ion. It's not going to add any acidic or neutral, things, or sorry, it's going to add neutrality to it. It's not going to add any acidic or basic nature to our solution. But we want it to still be a cation. Same thing with our nitrate anion, NO3, right? That thing is going to be neither basic, right, nor acidic. It's going to be neutral. But it's going to have that negative charge that we can have it go towards the buildup of positive cations. So what we need to know is that if we have a salt bridge, notice that our cations are going to flow towards the cathode. And our anions are going to flow towards the anode. So in our case, right, the NO3, the anions, right, are going to flow towards the anode, which is our zinc side. And our cations, the K, our potassiums, they are going to flow towards our, right, cathode, or the copper side there, to replenish, right? We're getting rid of some of those copper 2s, and we're getting less and less positive charge over there. So it's going to replenish some of that positive charge. That's how salt bridge works, is that it keeps the charge balance in check a little bit. And so it allows for the reaction to take place a little bit longer than it normally would be allowed to take place without that salt bridge present.